So for augmented and virtual reality application, we need full color microdisplay with a pixel pitch below 10 micrometer. And for that, we need efficient red, green, and blue micro LEDs. And the best would be to get them in a monolithic integration. So we need native color for the efficiency. And for the monolithic integration, we have to use the same material family. And so for that, InGaN is the best candidate, as it can theoretically cover the whole visible range by tuning its indium content. And as you know, it is possible to get monochrome microdisplay with the 3-nitride family from blue to red, but how to get those 3 primary colors in the same in a single epitaxy on the same substrate. So first about the efficiency. So we need efficient red, green, and blue InGaN micro LEDs, but there is a strong drop of the external quantum efficiency when the emission wavelength is higher than 500 nanometer. And this is mainly due to the alloy degradation when we increase the indium content. And this is due to the fact that the InGaN bulk is thermodynamically unstable for high indium content, and also because we are growing InGaN and GaN, and due to the high lattice mismatch between the 2 layers, the InGaN is in a compressive strain. And this leads to a compositional pooling effect or indium surface segregation effect. And for these 2 kinds of effects, the indium atom is always pushing away from the gallium nitride matrix, forming an indium reservoir on top of the surface. And finally, there is a limitation of the indium content when we are growing on GaN, and the limitation is at 25%. Also, in a PIN junction, the active zone is composed of quantum wells, and in the case of 3-nitride, there is a huge internal electric field in the quantum well, which reduces the transition energy, which is good to get high emission wavelength, but this is at the expense of the efficiency, as the electron hole wave function of a lab is reduced for thick quantum wells. And if we want to keep red emission while increasing the carrier density, as the internal electric field will be screened, we need well widths below 3 nanometer, with an indium content of 35% when we are growing on the C-plane of the voltage structure, or an indium content of 40% if we are growing on the semipolar plane or on the nonpolar plane. And so these values are very higher than the limitation that we have when we are growing on GaN. So how to enhance indium content in the InGaN alloy? So in the past, we grew full InGaN structure grown on an InGaN pseudo substrate fabricated by Soitec, which was called InGaNOS, and the substrate had various in-plane lattice parameters. And we grew different quantum well with different growth conditions that we call blue, green, amber, and red. And you can see that each time we have a redshift of the emission wavelength when we increase the in-plane lattice parameter of the substrate. And with this, we were able to cover the whole visible range by keeping thin quantum wells around 2.5 nanometer by playing on the in-plane lattice parameter of the substrate and on the growth condition of the quantum wells. And the effect behind this is that we are able to increase the indium content when the in-plane lattice parameter of the substrate is increased, and we were able to get 39% of indium content in a relaxed area of the structure. So to increase indium incorporation rate, we have to reduce the strain in the whole structure, and thus for that we have to use a full InGaN structure grown on a relaxed InGaN pseudo-substrate. So here you have an example of a full InGaN structure grown on InGaNOS. This structure emits in the red. You have the TEM images here in the quantum wells, and you see that the quantum wells are very disturbed. And if we want